Um, I talked about the idea of general solutions to trigonometric equations. That's when you have to put plus 2n pi on the end. Yeah, that's good enough. I talked about how do you use period and phase shift to study trigonometric equations. Basically, if you have something like sine of 3x minus pi equals 1/2, how you deal with an equation like that. I talked about quadratic trig equations. And I talked about how you can use Pythagorean identities. Section 6.3 was about the sum and difference formulas. There were a bunch of those in the textbook, like sine of A plus B, sine of A minus B, cosine of A plus B, all those sorts of things. I talked about how you use them to find something like sine of 75 degrees. Right, you can think about 75 degrees as 30 degrees plus 45 degrees, and use the sine of A plus B formula to find this thing. I talked about how you can find something like this. If we have like alpha plus 30 degrees, and we don't know what alpha is, but we do know, for example, that cosine alpha is 4/5. So I talked about problems like that, working with sum and difference formulas to solve problems like that. And also to do, like if I have sine pi over 5, cosine 2 pi over 5, minus cosine pi over 5, sine 2 pi over 5, how we can use the formulas to simplify something like this. So sort of the three types of problems I talked about using sum and difference formulas. And 6.4 dealt with the double angle formulas. And half angle formulas. Things like how do you find sine of 2 theta, how do you find tan theta over 2, those sorts of things. And again, there are a couple different problem types that came up in section 6.4 that basically correspond to this problem type and this problem type. So if you know sort of what the angle is, how can you use the formula to find that? Or if you know that like cosine alpha is something, how can you use the formula to find that? And then the last section we covered in chapter 6 was section 6.6, which was about the sine inverse, cos inverse, tan inverse functions. So I talked about, firstly, problems like how do you find sine inverse of negative 1/2, right? How do you find that sort of thing? I talked about problems like how do you find the cosine of sine inverse of negative 1/2, right? So if you've got like a sine inverse of negative 1/2 and then try to find the cosine of that, how you do something like that was something else I talked about. I talked about how to graph these sorts of things. Right, so how do you graph a transformation of cos inverse, sine inverse, or tan inverse? And I talked about how you use these things to solve equations. So if I have sine x plus 1 equals 2, or equals y, I'll say, right, how you can solve that equation for x. You move the 1 to the side, you'll have sine x equals y minus 1, so x is sine inverse of y minus 1. Okay, so that was what we covered in chapter 6. Any questions about from chapter 6 material before I move on to start going on to chapter 7? Okay. So Chapter 7 had two sections, 7.1 and 7.2. 7.1 was about law of sines, and basically how we use laws of sines to solve triangles, to find different angles and such in a triangle. 7.2 was about the law of cosines, and solving triangles, right? And then I did a section on word problems from both those sections. Right? How do you solve word problems that use either law of sines or law of cosines in them? So Chapter 8 was next. Again, there's only two sections we covered from Chapter 8. So Chapter 8.1 was about solving systems of equations by substitution. And again, substitution is where you have something like y equals 3 minus x, and every time you see a y, you replace it with 3 minus x. Right? That's this idea of substitution. That's what we covered in section 8.1. And again, a system of equations is just two different equations together. Like x plus y is something, x squared plus y squared is something else. 8.2 was about solving linear systems by this method that's called elimination. And elimination means we add or subtract one equation from the other in order to get rid of things. One thing to mention that, again, sometimes people forget to study is the notion of how do you know how many solutions a system of equations has, right? The idea about if you get something like 0 equals 1 when you try to solve, it means the system of equations has no solutions. So the number of solutions is 0. If you get a single solution, obviously there's just one solution. If you get two solutions, and obviously there's two solutions. And if you get an equation like 0 equals 0 or 1 equals 1, the system of equations has infinitely many solutions. There's lots of solutions that are out there. So knowing sort of how we talk about the number of solutions in those situations and how to know how many solutions are going to be is important. Oh, hi. And then again in Chapter 8, there was also a section on word problems. Basically, how do we take a word problem and turn it into equations so that we can solve it. And I talked about the ideas of how to figure out what the unknowns are, how to figure out what the equations are, that sort of thing. And then the last thing that we covered this week was Chapter 9. Section 9.1 is on sequences. So I talked about formulas for sequences. Say something like an equals n over n plus 1. Right? This is saying that the first term in the sequence is going to be 1 over 1 plus 1. Second term is going to be 2 over 2 plus 1. Third term is going to be 3 over 3 plus 1, etc. I also talked about what are called recursive formulas. That's the formula where we use one term to get the next term. So like ak plus 1 equals k times ak. That's an example of a recursive formula, because to find one term, we need to know the term before it. I talked about sigma notation, how we read something that has a sigma in it. Oh, shoot. Okay, anyways. And 9.3 dealt with geometric sequences. And basically, what you need to know in 9.3 is basically how to use the three formulas for geometric sequences. The first one says an equals a1 r to the n minus 1. The second one says Sn equals a1, 1 minus r to the n over 1 minus r. And the third one is S equals a1 over 1 minus r. So the first one is the formula for the nth term of a geometric sequence. How do we know what the 10th term is, what the 15th term is, if we know the a1, which is the first term of the sequence, and the r, which is what we're multiplying by each time in a geometric sequence. The second formula gives you how do you add up n terms of a geometric sequence. And this third one is if you're adding up an infinite number of terms of a geometric sequence. And again, what I just remembered is that those are going to be on the formula sheet. I have not actually typed them up into the formula sheet yet. I said I would do it before class today. I haven't yet. I will do it immediately after class today, and I will upload the new formula sheet to the course web page later today. So if you look at the formula sheet, it will have those three formulas on it as well. I'm not going to expect you to memorize those formulas. Yes, go ahead.
Do we bring that in with us, or
it will be the last page of the exam. So yeah, the formula sheet will be the last page of the exam. So you won't need to bring one in with you. Yeah. And if you want during the exam, you can pull that last page off. That's why I used to put it as the second page of the exam after the cover page, and then people always tried to pull them out and would like rip off the cover page while they're doing it. So this time it's going to be the last page, so you can pull it out of the exam booklet and not have to worry about losing it. Okay. Any questions about what we covered in chapter 7, 8, and 9? Great. Okay. So now I'm going to go back and I'm going to review all the stuff from the beginning of the course, everything up until the first test and the second test. So again, that was chapters 1, 2, 3, 4, and 5. Okay. So chapter 1, that was the very first step in the course. That was generally basic algebra stuff. Section 1.1 was on real numbers. There was things like absolute value in there, what the absolute value means. There was things like if you have a positive number over a negative number, you get a negative number. Those sorts of ideas were all in section 1.1 on real numbers. The chance of there being a problem that's only from section 1.1 is fairly low on the exam, because most of the stuff that I used in section 1.1 I used in more advanced ways later. So the chance of you seeing a problem which is just like, you know, if you have a positive number over a negative number, is it positive or negative? That's unlikely to actually be an exam question. So this one, yeah, I mean, if you're having trouble using the stuff that uses the absolute value, for example, like how to graph the absolute value function, you can go back over 1.1 to understand the absolute value function, but again, the questions I'm going to ask are usually going to be a little bit more difficult than the 1.1 questions. The big thing in section 1.2 was the laws of exponents, and I think radicals were in that one too. Sorry, I just go back to the table of contents to make sure I remember. Yes, laws of exponents and the laws of radicals. So things like if I ask you to simplify square root 8 plus square root 18, right? The fact that you can write the 8 as 2 times the square root of 2. The square root of 18 is 3 times the square root of 2. And then 2 times the square root of 2 plus 3 times the square root of 2 is 5 times the square root of 2. So being able to simplify something like this is using laws of radicals, and that stuff that was in 1.2. Oh, also the notion of rationalizing was in section 1.2. So if we have like 1 over square root of 3, the idea that we can rationalize the denominator, we're multiplying top and bottom by square root of 3. That was in there, in section 1.2. Section 1.3 was on algebraic expressions. And again, most of it was simplify problems. So algebraic expressions are things like x squared minus 4 over x squared minus 9. right? How would you simplify something like this? Well, you can factor the top and bottom, see if anything cancels, right? How would we add this to 4 over x? Well, we'd have to multiply, put them over a common denominator, right? You have to multiply top and bottom of this by x, have multiply top and bottom of this by x squared minus 9. So the idea of those sort of simplification methods, how you simplify rational expressions, that all that algebra was in section 1.3. Section 1.4 was on solving equations. This was like the longest section in chapter 1, and in some ways the most important. We've done a lot of questions like 1.4 questions as part of other questions later on. But if you're having difficulty solving equations, if you know it's something you have difficulty with, go over section 1.4. In here there's like quadratic equations. There's what are called rational equations. A rational equation is something like 1 over x plus 1 equals 3 over x plus 2. Like how you solve something like that. There's things with square roots in them. There's things with absolute values in them. Right? What else? Oh, things like x to the 7th equals 6. Right? How you solve an equation like that. So a whole bunch of different types of equations in section 1.4. And I think it's a fairly important section to go over, because not only is this stuff used in section 1.4, it's also used later on as parts of other problems. Section 1.5 was on complex numbers. Basically, how do you add them, how do you subtract them, how do you multiply them, how do you divide them. That's the most important thing in that section 1.5, is knowing how to add, subtract, multiply, and divide complex numbers. And section 1.6 was on inequalities. Things like, how do you solve this inequality? Right? X squared is bigger than x minus, actually we'll make that a 6. Plus 6, sorry. How do you solve something like this, right? The idea is to solve something like this, you've got to move everything to one side. You've got a factor, but then you've got to use this thing called a sign table. Right? I don't know if you remember that, where you sort of figure out where it's positive or negative by plugging in different values in different parts of the number line. So this section 1.6 is where we talk about sign table and solving inequalities. Things like this, absolute value of x plus 1 is less than or equal to 4 were also on there. I know absolute value signs always confuse a whole bunch of people. This is not difficult, solving an absolute value inequality like this, but it is confusing if you don't remember how to do it. So again, try to make sure you go over that sort of stuff in the inequalities section. Any questions about the chapter 1 stuff before we move on to go over chapter 2? Okay, so chapter 2, section 2.1 was about graphing points, right, like how do you figure out where 1, 3 is. There was also a couple formulas in there. There was the distance formula and the midpoint formula. Those might be useful to you. There was also sort of things like understanding what x is bigger than or equal to 0 represents. So this represents the right-hand half of the plane. Because if x is non-negative, that means the x-coordinate is to the right of the y-axis. Those sorts of things were in there as well. 2.2 was graphing equations. The hardest thing in this section was circles. Again, a lot of this 2.1, 2.2 stuff was really easy if you've done sort of any high school math. It's just sort of, plug in values, make a table of values, connect the dots. But the circle stuff, I know there's a number of people who had difficulty with working with circles. So go over the stuff on circles if you've forgotten it. Section 2.3 was on lines, right? What is the equation like y equals mx plus b represent? There was also like the point slope form, that sort of thing, right? So if you know the slope of a line, you know a point of the line, you can find an equation for a line using the point slope form. The idea of what a slope represents, what an intercept represents. And there were also some word problems in section 2.3 you might want to take a look at. Section 2.4 was about functions. So there was things like the definition of a function. There was also stuff about using function notation. Right? If you're doing something like f of x plus h, that means that every time you see an x, you replace it with an x plus h. Right? Those sort of stuff, that's all section 2.4 stuff. Domain and range is in here as well. So knowing how to find the domain of a function is going to be important. Again, I'm not going to ever ask you to find the range of a function without using your graphing calculator or using some other method of graphing it. I'm never going to ask you to find the range without graphing something. But the domain I can ask you to do without graphing it. Because the domain, just look for places where the bottom is 0 or the inside of a square root is negative, those sorts of things. Section 2.5 was what's called graphs of functions. There were basically 3 topics in here. There was symmetry, right? How do you tell if a function has symmetry, if its graph is going to have symmetry? And again, here I talked about even and odd functions usually when I talk about symmetry. There were piecewise functions, right? How we graph piecewise functions, and then there were transformations. Again, the transformation stuff I've gone over like in almost every chapter after this one. I did transformations in chapter 4 and chapter 5 and chapter 6. So if you still don't sort of understand how to use transformations to sketch a graph, it's definitely an important subject, and please go back and go over it. Hopefully I've gone over it, not that everyone gets it by now, but if you don't, yeah, this is where the basic information about transformations is for you to go over. .6 was about quadratic functions. Here the main topic is the vertex of a quadratic function, how you find the vertex. And again, to mention the easiest way to find the vertex is this thing called the vertex formula. So look that up if you don't remember what it is. And basically, how do you graph quadratic functions? Oh, where was it? Anyways, I realized, I think it was in chapter 2.6 or 2.4 is where arrow notation first came up. I didn't sort of mention it because, again, it's come up like all the time throughout the course. It's another thing like the transformations that I've been doing in every chapter. If you still don't understand what arrow notation represents, go back to section 2.4. That's where it was, but... And then the last thing in chapter 2 was section 2.7. Which is about operations on functions. Things like what happens if you add two functions together, what happens if you subtract two functions, what happens if you multiply them, what happens if you divide them, and what happens if you do this thing called composition. Right? There's 5 different ways that we can combine two functions together. And the other thing that came up in this section that everyone seemed to find difficult is domain and range. How do you find the domain and range of something if it's created as a composition of two functions? Actually, sorry, just domains. I didn't talk about ranges. I did not talk about the range of a composition, just the domain in section 2.7. Any questions about the chapter 2 stuff before I move to going over chapter 3 stuff? Okay. By the way, one thing to mention, if you look at the handout I gave with the distribution of questions on the exam, you will notice there are more chapter 2 questions than there are chapter 1 questions. In fact, I think there's even more chapter 2 questions than there are chapter 3 questions, more chapter 2 questions than there are chapter 4 questions. Again, it's just because chapter 2 is a particularly important chapter, so try to, and there was a lot of material in chapter 2, so try to make sure you do go over that. So chapter 3 was where we dealt with polynomial functions and rational functions. So 3.1 was about polynomial functions, right? How do we graph them? So how do we graph something like x cubed minus 2x squared plus 3x minus 6, right? So using, we talked about this idea called the leading term test, which says that if we have something like negative 3x to the 4th, the negative 3 tells you the right end goes down, and the x to the 4th tells you both ends do the same thing, right? That if you know the number in front of the first, even if we had like a plus 4x squared minus 7, right? It's the first term that tells you what the ends of the graph do. That's that thing called the leading term test. 3.2 is basically about long division of polynomials. That's basically what you need to know how to do from section 3.2 is how do we do long division of polynomials. And 3.3 was about zeros of polynomials, right? How the relationship between zeros of a polynomial and factors of a polynomial and x-intercepts. This notion of multiplicity was in there. Those sorts of things were in section 3.3. Again, a lot of sections 3.2 and 3.3 I didn't cover. I did not cover all of 3.2 or all of 3.3. If you want to see what I did cover, go over the slides or go over the handouts. And then to finish off chapter 3, I did 3.5, which is about rational functions. How do we find asymptotes? How do you find holes in a graph? And how do you graph rational functions? Again, rational functions are things like x squared minus 4 over x squared minus 9, right? Because it has both a polynomial on the top as well as in the bottom. That's a rational function. Yeah. Again, if you notice, there's on the list of type of questions that are on there. There will be one graphing question from chapter 3. It'll be the hardest of the graphing questions. It'll either be obviously polynomial function or rational function graphing question, because those are the 2 topics that came up in chapter 3 involving graphing. Okay. Any questions about chapter 3 before we move on to chapter 4? So section 4.1 was about inverse functions. So I talked a bit about the idea of an inverse, which is what happens if you switch the x and the y. Right? So you can think about switching the x and y coordinates in a graph, or you can think about switching the x and y variables in an equation. I talked about the notion of one-to-one functions, right? What it means for a function to be one-to-one, what that tells you about an inverse. I talked about finding a formula for an inverse algebraically. Right? How do we find a formula for an inverse of a function? By switching the x and y variables and solving. I talked about the domain and range of an inverse. And what was the other? Oh, yes. What happens if you take a function composed with its inverse? The idea that if you take a function, if you do an inverse and you do the actual function, you should get back exactly to where you started. So that was section 4.1. Section 4.2 is about exponential functions. How do you graph them, right? How do you graph exponential functions? And the other thing in section 4.2 was about solving equations like, right, if you have 2 to the x equals 4 to the x minus 2, you can solve an equation like that by writing the 4 as 2 to the 2. And that'll allow you to solve an equation like that. 4.3 was about the number e, and how you graph something like y equals e to the x minus 6. Right, how you graph something like that. And that was section 4.3. Section 4.4 is about logarithms. How do you switch between exponential form and logarithmic form of an equation? And that's sort of the basic thing you can do with logarithms. I'll talk about what ln means, what log with nothing after it means. I talked about how you find something like log 2 of 16. I think graphing was also in here in 4.4. Oh, and solving something like log 3 of x equals 2 was also in section 4.4. How do you solve a simple equation like this? The answer is you switch it to exponential form. You replace the log 3 on this side with the base 3 on the other side. Those sorts of ideas. Section 4.5 was about properties of logarithms. Basically, how do you simplify things using properties of logarithms? That's the main sort of topic. So if we have something like log 3 of x squared y over z cubed, right? How I can simplify something like that by writing it as log 3 of x squared y minus log 3 of z cubed, moving the exponents out front, that sort of thing. And 4.6 was about solving equations. There were both equations like log 2 of x plus log 2 of x plus 1 equals log 2 of x plus 3, right? There were equations like that where we had like multiple logarithms on both sides, and we had to solve them by combining these two logarithms together. And there were also equations like 2 to the x plus 1 equals 3 to the x. Right, equations where you have to take the logarithm of both sides in order to solve the equation. So that's what section 4.6 was about. Any questions about chapter 4 before I move on to chapter 5? Okay. Oh, you know what I'm going to do? I realized I forgot to do it earlier. I mentioned yesterday that I was going to bring chocolate for everyone. I'm going to pass them around. So here's a bag of Easter eggs for this side. Here's a bag of Easter eggs for this side. Feel free to grab a couple and pass them around. Hopefully it'll help keep people awake and alert. It is a stimulant, so it is good for studying, and supposedly it makes your brain work better, according to some research. Yeah. But anyway, I just was like, I need to do something to wake you folks up. I just want to make sure the recording's still working great. Okay, so chapter 5. Section 5.1 was about angles. Main topic sort of was degrees and radians and how to convert from one to the other. There was the idea of coterminal angles, what a coterminal angle is, and how it's, like the idea that 360 degrees and 0 degrees are coterminal angles because they both give you the same place, just two different ways of getting to the same place. And then there were some formulas for arc length and area that were in there that involved angles and radians. Section 5.2 was about trigonometric functions. So it started off with SOHCAHTOA, right, and how we define trigonometric functions that way. There was the idea about talking about trigonometric functions using the coordinate of the point and the distance r from the origin to study trigonometric functions. That was in there too. I talked about the functions secant, cosecant, and cotangent, how those guys are defined. I talked about the Pythagorean identities. Right? What sort of relationship, like sine squared plus cos squared equals 1, secant squared is 1 plus tan squared, those sorts of things. And the sort of the key problem from section 5.2, which again is key because it comes up in a whole bunch of other sections, is the idea is like if we know that cosine alpha is 4/5 and we want to find cosecant alpha, right? The idea that we can do so by sort of drawing a point in the plane where this is the x-coordinate, this is the radius, figuring out where the y-coordinate is using Pythagoras, and then figure out what cosecant of alpha is. Again, this type of problem is one that comes up again and again and again, and varied by many different sections. And so it's going to be important to go over. Then, 5.3 talked about the unit circle. So here's where I sort of talked about the special angles. The 3 special angles you basically need to memorize. I talked about how to find things like cosecant of -3 pi over 2. right? By sort of visualizing that negative 3 pi over 2 is negative 270 degrees. You get up to the top of the circle. You can figure out what the x-coordinate, y-coordinate is at the top of the circle. Find cosecant there. I talked about all your basic trigonometric graphs in this section. Sort of what does the graph of sine x look like? What does the graph of cos x look like? What does the graph of secant x look like? Section 5.4 was about the idea of reference angles. Right? The idea is that if you have an angle here, and you want to know what the sine and cosine of it is, you can figure out what these sine and cosine are by using an angle over here that's exactly opposite that angle, right? Finding what's called the reference angle back here. And there were two types of problems I talked about using reference angles. There's something like this, right? We want to find the cosecant of an angle. And the second type of problem is something like this. We know what the sine is, we want to find the angle, right? So these are sort of finding what is cosecant of this. This is figuring out what theta is if sine theta is this. I talked about how to do both those types of problems using the idea of reference angles to study them. Section 5.5. So section 5.5 is about graphing sine and cosine graphs. And the main concepts here was a period of a graph, the phase shift of a graph, the amplitude of a graph, those sorts of things. And 5.6 was about graphing tangent, cotangent, secant, and cosecant graphs. And you're applying those same sort of notions, applying period, phase shift, amplitude to do graphs of those guys. And that's where, again, I did the chapter 6 and chapter 7, chapter 8, chapter 9 stuff already before we went over this stuff. So that's what was in the course. Again, it's a lot of material. It's been a long course. Again, one of the annoying things about this course is that it covers basically all of grade 12 math and some of grade 11 math in only one semester. So it is a dense course. There's a lot of material. Hopefully you've been doing enough studying over the course of the semester that you have a bunch of this stuff down already. You do still have 2 weeks before the exam. So you do definitely have time to do more studying if you need to. Again, I'm going to go over what's on the Muddy's Point card still. If you are not interested in hearing what's on the Muddy's Point card, you're totally free to go. If you have assignments to hand in, please just throw them up on the desk here. Yeah, and then basically I'm going to go over what's on the Muddy's Point cards, and then I'm going to go over any other topics folks want me to go over. So review by request at the end. Anyone have any questions before we move on to talking about Muddy's Point cards? Okay, you're welcome. Yes. Yeah. Oh, and just a reminder for everyone, I realized I should have gone over this again. I am having office hours the day before the exam from 12 to 2. So if you have any questions you want to ask in person, that's the time to do it. Otherwise, I will be checking my email. I will be out of town next week for a good part of the week, but I'll definitely be checking my email just after Easter weekend. So that Monday. Or no, Easter Monday's a holiday, so Tuesday probably I'll check my email. Okay. Okay. So I'm going to start going over the muddiest point questions. The first one that I have on there is this. Suppose I want to find arc sine of 13 pi over 9. Now normally we would expect these two things, the arc sine and the sine, to just cancel each other out. That was going to be the easy way of doing this problem. The problem with this one is that 13 pi over 9 is outside the range of sine inverse. Again, arc sine is another fancy word for sine inverse. It's another fancy word for sine to the negative 1. The range of sine to the negative 1 is between negative pi over 2 and pi over 2. Because 13 over 9 is bigger than pi over 2, the answer cannot be 13 over 9. I cannot cancel those two things. So what I've got to do is I've got to figure out, okay, where is 13 pi over 9 on the unit circle? 13 pi over 9 is bigger than pi. It's bigger than 9 pi over 9. It's is it smaller than 3 pi over 2? 3 pi over 2 it would be 13.5 pi over 9, so yes, it is smaller than 3 pi over 2. 13 pi over 9 is approximately here. So what I want to do is I want to figure, okay, sine of 13 pi over 9 is going to be the y-coordinate of this point. That point on the y-axis is sine of 13 pi over 9. And if I want to find arc sine of this number, I want to find the angle which is in this range, which has this thing as its sine. Right? So it's got to be in that range. It's got to be somewhere between here and here. Right? If it's in the range of sine. And it's got to have this thing as its sine. So I'm taking arc sine of this, so I want to have that as its y-coordinate. So what I'm really looking for is this blue angle down there. That is the same sign as the red angle. That's what I'm going to be looking for. So the first thing I'm going to do is I'm going to find the reference angle. The reference angle is going to be directly opposite 13 pi over 9, so it's going to be 13 pi over 9 minus pi. Pi we can think of as 9 pi over 9. So the reference angle here is 4 pi over 9. And this blue angle down here is going to be the negative of the reference angle that goes up. So this blue angle is negative 4 pi over 9. So the arc sine of sine 13 pi over 9 is negative 4 pi over 9. The idea is we want to visualize what is sine of 13 pi over 9. It's that y-coordinate there. And if we're doing arc sine of that, we want an angle which has that as its y-coordinate, but is in this range. So we want to find an angle which has this y-coordinate, which is between negative pi over 2 and pi over 2. It's got to be that blue angle. How is the blue angle related to the red one? It's a mirror image of it. So first find the reference angle, then take the mirror image down there. Any questions about how I did this one? Okay. The next nice point I'm going to do here's an equation. I want to find all solutions to this equation. So first I'm going to divide both sides by 2 square root of 3. Actually, I'm just going to write it as 2 over 2 square root of 3, which simplifies to 1 over the square root of 3. Then I'm going to sort of think of the 1/3 t as a theta. right, and try to figure out what theta is. Well, if I draw my unit circle, oh, know the angle. If I go to the angle pi over 6, the cosine is square root 3 over 2, the sine is 1/2, and the tangent of pi over 6 turns out to be 1 over square root of 3. So pi over 6 is one possible value for theta. There is another angle which has the same tangent. It's going to be this one down here. This one is opposite pi over 6. This angle is pi plus pi over 6, which turns out to be 7 pi over 6. So one possible answer is pi over 6. The other possible answer is 7 pi over 6. So there's two different ways of writing the solution for theta here. I can either write it as theta is pi over 6 plus 2n pi, comma, 7 pi over 6 plus 2n pi. That's one way of writing the solution. Another way is writing it as pi over 6 plus n pi. Because 7 pi over 6 is just pi over 6 plus pi. So rather than adding 2 pi, multiples of 2 pi to each of those, I can multiples of pi to pi over 6. Now we're not done yet, because what we found is we found what theta is, and we want to find what t is. I'm going to use the second solution to find what t is. It's going to be a little bit faster than using the two separate solutions. So if I'm using the second solution, I have that 1/3 t equals pi over 6 plus n pi. Then I want to multiply both sides by 3 to cancel off that 1/3. So I'll get t, pi over 6 times 3 is pi over 2, and pi times 3 is 3n pi. So that's the general solution, pi over 2 plus 3n pi. Any questions about what I did on that one? Okay. So, get another card full of buddy's points to go over. I'm going to look for other trig ones, and I'm going to do any other trig ones first, and then I'll move on to the other sections. So, trig ones I've got here. Graphing inverse trig functions. Yes. Sorry. Yeah. Okay. So if I want to graph, for example, that guy. 3 cos inverse of x minus 6. The first thing you need to figure out is what does the graph of cos inverse look like? Well, the graph of cosine looks like this. Right? That's the graph of cosine. If we want to find cos inverse, the key thing is that first we take a part of the graph of cosine. What part are we taking? Well, that's what depends upon what the range of cos inverse is. The range of cos inverse is from 0 to pi. So we take the part of the graph of cosine, which goes from 0 to pi. So there's 3 key points on that graph. This one's at 0, 1. This one's at pi over 2, 0. And this one's at pi, negative 1. And if we want to get the graph of cos inverse, we just take those 3 points and switch the x and y coordinates. 0, 1 will become 1, 0. 0 pi over 2, 0 will become 0 pi over 2. And pi negative 1 will become negative 1 pi. And that's what the graph of cos inverse looks like. And again, if you want to get the graph of cos inverse, start with the graph of cosine, switch the x and y coordinates. That's how you get the graph of any inverse function. by switching x and y coordinates. Then I've got to do transformations. This is a vertical stretch by 3, and I've got to move it right 6 units. So if I do that, vertical stretch by 3, I'll just do it to each point. So 1, 0, vertical stretch by 3, the 0 is not going to change, but if I move it right 6 units, it'll become 7, 0. 0 pi over 2, vertical stretch by 3, you multiply the pi over 2 by 3, you get 3 pi over 2. Right 6 units, it'll go to 6, comma, 3 pi over 2. And if we take negative 1 pi, vertical stretch by 3 will give you negative 1, 3 pi. Right 6 units will give you 5, 3 pi. And that's what the graph's going to look like. Any questions about that example? Okay. Next, there's a couple equation solving questions I want to do. Again, I've got a lot of these points to go over, which is one of the reasons that I'm kind of doing it rapid fire like this. If this isn't working for you, please feel free to interrupt me and ask me questions, get me to explain things slower, that sort of thing. I just want to make sure I have a chance to go over everything that's on the cards before the end of class today. So I've got a couple different equation solving questions I'm going to do. The first one is things with rational exponents. Let's say you've got something like that. 2x to the 1/2 minus 7x to the 1/4 plus 3. So this is an equation solving problem, right? You want to solve this equation. The key thing here, and it looks sort of like a quadratic equation, right? We've got 2 different powers of x here. But the way it's written, it's not a quadratic equation. So our goal here is going to be to turn it into a quadratic equation. When we do that, we want to figure out what's the smallest power of x and call that thing y. This is the smallest power of x, so I'm going to say here that y equals x to the 1/4. What is y squared? Well, if we do x to the 1/4 squared, that gives you x to the 1/2, because 1/4 times 2 is 1/2. So this will become, that first term will become a 2y squared. The middle term will become a 7y. And then we need to factor that thing. And we're factoring something like this. We multiply the first term by the last term. That gives you 6. We want two things that multiplies to 6, adds negative 7. That turns out to be negative 6 and negative 1. So we'll have 2y squared minus 6y minus 1y plus 3 equals 0. And then we've got to solve that thing. Take a common factor out of the first 2 terms. That common factor is 2y. Take a negative 1 out of the last 2 terms. You get something like that. 2y times y minus 3 minus 1 times y minus 3 is 0. Take out a y minus 3. And we get that. So then either y minus 3 is 0 or 2y minus 1 is 0. Here it means y is 3. The second one is y equals 1/2. Now then we need to remember that y was x to the 1/4. So really we have one of two situations. Either x to the 1/4 equals 3, or x to the 1/4 equals 1/2. If we want to solve those things, we've got to put each side to the fourth power. X to 1/4 to the fourth is just x. 3 to the fourth is 81. X to 1/4 to the fourth is just x. 1/2 to the fourth is 1/16. So those are two solutions. Either x is 81 or x is 1/16. I'm realizing I only have like 10 minutes left. I am not going to have time to go over all of these. So if whoever submitted the card wants to like talk to me after class or whatever and go over the rest, that's totally fine. I'm going to do 2 more, and then that probably will be enough. That'll probably be our time for today. So the next question I want to do I'm going to do it this way. Okay. That sort of equation. So the key thing is if we have a logarithmic equation and we have more than one logarithm on the same side, what we need to do is we just take those 2 logarithms and then combine them together. The key thing you need to know is you need to know laws of logarithms. So laws of logarithms says if we have log of something plus log of something else, that's the same thing as log of the first thing times the second thing. Then, x times x plus 1 is x squared plus x. And now, since we have log of something equals log of something else, the things inside have to be the same. X squared plus x is 2x. Move the 2x over. X squared minus x is 0. Factor. We factor out an x. We're left with x minus 1. So either x is 0 or x is 1. And logarithmic equations is one of the types of equations where we need to check our solutions. Those might not be solutions, and the reason they might not be solutions is sometimes if you plug them into the original equation, we cannot do what we get. So here, if I plug in x equals 0, I get log of 0 plus log of 1 equals log of 0. And the thing is that log of 0 does not exist. You cannot take the logarithm of a number that's not positive. Yeah, you cannot take the logarithm of 0, you cannot take the logarithm of a negative number. So log of 0, that does not exist. So x equals 0 is not a solution. Next, we can try x equals 1. Here it will be log 1 plus log 2 equals log 2. Well, all those things you can do. I can do log 1. I can do log 2. I can do log 2. So those all work. So x equals 1 is a solution. So again, logarithm equations are one of the types of equations where we need to check our solutions. The other ones are equations with square roots. We need to check our solutions. Equations with fractions. With rational expressions with fractions and x in the bottom. We need to check our solutions. It's possible to get this sort of thing that looks like it's a solution, but turns out to not be a solution once you plug it back in. Okay. I think the last thing I'm going to go over from the Mighty Point cards is finding domains of arithmetic combinations. So, let me do a f of x equals 1 over x squared minus 4. G of x equals square root x minus 1. Actually, I'll do it the other way. So here's f of x, there's g of x. I want to find the domain of g over f of x. So the first thing to do if you're ever doing a domain of something like this, figure out what is the domain of f of x, what is the domain of g of x. Well, here if we're doing the domain of f of x, it's a rational function, so whatever's on the bottom cannot be 0. So we got that x squared minus 4 cannot be 0. So x squared cannot be 4. So x squared cannot be plus or minus 2. That's what the domain of f of x is. Right? So if you go to rational expression, something with some x in the bottom of the fraction, then whatever's in the bottom cannot be 0. If we're doing the domain of g of x, we have a square root. If you ever have something with a square root, whatever's inside the square root cannot be negative. So we got that x minus 1 is bigger than or equal to 0. So x is bigger than or equal to 1. So usually if we had just g plus f, g times f, g minus f, all we do is you put these two sets of restrictions together. We say, let's say, okay, x cannot be any of these things, it has to be bigger than or equal. Oh, what? 0? Sorry, 1. We have 1 to both sides. Anyways, we would put these two sets of restrictions together and say, okay, what could x be? If it can't be plus or minus 2, it also has to be bigger than or equal to 1. What are the possible x values? Because we have g over f, there is an extra restriction. Whenever we have g over f, there's an extra restriction. The extra restriction is that whatever's on the bottom cannot be 0. So here there is an extra restriction, and this extra restriction is that f of x cannot be 0. What is f of x? F of x is this. Yes?
Should that not be x squared?
Ah! Yes, thank you. That should be x not equal to plus minus 2. Thank you. Thank you, Brant. Multiply both sides by x squared minus 4. I get 1 does not equal 0. Well, this isn't a restriction. It's always true that 1 does not equal 0. So we don't have to worry about this restriction at all. But we do have to worry about these two. So the idea is what we do when we're trying to find the domain is usually we want to write the domain in what's called interval notation. So I'm going to start by drawing a picture of the domain. Right? So here's my number line. Here's 0. X cannot be negative 2. So negative 2 is out. X cannot be 2. So 2 is out. X also has to be bigger than or equal to 1. Right? Since x has to be bigger than or equal to 1, that means that everything down here is out. Right? Because x has to be bigger than or equal to 1. So I forget about all that part of the number line. What's left? Well, it's enough to the little piece here between 1 and 2, and another piece beyond 2. The piece between 1 and 2 is that interval. From 1 to 2, 1 is included, 2 is not included. Together with a piece from 2 to infinity. Again, 2 is not included in that piece because they put an x where the 2 was. X is not allowed to be 2. And there we go. That's the domain of g over f of x. So again, if you want to find the domain of a combination of two functions, find the domain of the first, domain of the second, put them together. Yeah, there's only 2 minutes left. I'm going to stop here. I don't want to try to squeeze something in the last 2 minutes. If anyone has other questions for me, feel free to ask. And again, the first thing I'm going to do after class today is fix that formula sheet. If anyone has anything they want to ask me before the exam, feel free to send me an email or come by my office hours from the 24th. Yes? Oh yeah, if you have assignments, throw them on the pile here. The pile of assignments right there. Oh, sorry, a question about the assignment. Yes. Yeah, if I'm honest, it's not for non-writing. Okay, yeah. Yeah, as long as I can, yeah, it's legible. So, yeah. Thank you. Oh. There is one here, I think. Is this the one? Yeah. Sweet. Even though it's not mine. There's a stapler here. Yeah, I don't know whose desk this is, but Yeah. Faculty. Yeah. Just kind of pile. Yes. Oh, well, you used to gotta take the 7th root of both sides. So if it's x to the 7th equals 6, you just do a 7th root here, and a 7th root here. So x is the 7th root of 6. Yeah. Yeah. Uh-oh. Here it is. I was like, it wasn't it wasn't a backpack. I brought it to class. Yeah. There we go. And yes, you can have this back if you want. Because like I do the last.
I don't have any questions, but I just wanted to make sure I'm doing it right. But I feel like
I'm just checking with your answers.
Yeah.
They look pretty good.
a couple of us got the same.
Yeah, exactly. If you got the same for that answer, it probably means you did it right.
Yeah.
Yeah.
Thanks.
And the triangles look good and the work is good. Yeah. Okay, thank you.
Probably the same kind of thing. Is there a lot of approximation in this?
Yes.
Yes.
They're not going to be. None of them are going to be exact answers.
Okay,
Yeah.
good. The other question, does it totally match the image?
No.
No, okay, because
That's the other thing too. Is
I got an
realized-
angle, I'm like, that's weird.
Yeah. No. If you actually look at like what I said was to 50 degrees, that is not. Oh, actually, this picture's. Yeah. Sorry. No. 50 plus 30. Sorry. These angles are both smaller than what I drew.
Yeah.
Because 50 plus 30 is less than 90, and I made
And you
it bigger
said
than 90.
that this actually is a part of the triangle. That was just to show the
That's
north,
just
right?
that was just to give the Z thing and give you the 50 there. That's what that one was for. Yeah.
When and where was the final exam again?
Oh, Friday the 25th, which is 2 weeks from today, 2 to 5 p.m.